Can you see now?
Yes, now you can. We can see your slides, Matteo. So please.
Okay, perfect. So my name is Matteo Repetto from CNR, which is the largest research institute in Italy. We are around 7,000 researchers here, and I am the coordinator of the Miranda project. And I'm a research scientist at CNR working in cybersecurity issues, especially for what concerns visibility, orchestration aspects. So Miranda started almost 2 years ago in September 2024 for a duration of 3 years, like many other projects, with a total budget of around 7 million euros, 14 partners and 3 use cases. So we are a well-balanced mix of both industries, SMEs, and also some universities and research centers to bring the necessary long-term perspective to this innovation action. We cover several countries in Europe, as you can see here. So, what is the main concept for Miranda? Miranda builds on the concept of digital services and most of all of their interconnections. So we have a lot of services deployed around us, cloud services, IoT devices, network infrastructures, cloud services, data sets, and these are incrementally connected by different kinds of relationships like APIs or even other kind of manual relationships, let's say. So this creates a lot of dependencies and what is called, the supply chain. So the basic understanding is that there are a lot of threats coming from the supply chains, and also there are surveys out there that estimates how much organizations have already been affected by threats in the supply chain and also will be affected in the next year. Probably the most known aspects about the supply chain is the security of a software supply chain, but we moved the scope in a different direction. So we broadened the scope to the service supply chain, which is a bit different from the software supply chain because we move the scope from the development perspective to the operation perspective. So we are interested in the threats and attacks that can come at runtime, not only in the development of the software, but also in its operation. And also the scope goes beyond the plain software because we also look at running services like infrastructures, cloud infrastructures, telecom infrastructures, and things like that. So the purpose is to improve the current practice here in Europe, where we have currently the NIS2 directive, and we found that this directive has some limitations, probably derived from the current lack of collaborative cybersecurity operations. So basically, if you look at how this directive is implemented in the member states, we found that usually it is limited to the identification of suppliers in your supply chain, and this is something that it's not done automatically, but you must register manually your suppliers and update every year this list. Also, the scope is quite narrow so far because it only addresses the operators of critical and essential services. Okay, we all agree that these are the most critical entities in Europe, but often threats also affect other kinds of entities and organizations. So it is important that the framework is more scalable and more easy to be used by everyone. And finally, we noted prevalent reactive, static, and fragmented approach, where each provider is expected to report cyber incidents, to perform some kinds of cybersecurity obligations, and also to implement risk management. But these often are operations carried out by each provider independently, standalone, without a lot of collaboration with the others. And also the only kind of collaboration expected so far is in a hub and spoke manner. So everyone is expected to report. And everyone is expected to report to the national authority, but there is no direct interaction between providers. So what is the concept of Miranda? We start from the consideration that, okay, it may be quite simple to create an overview to discover interconnected services to my application, to my system, to my framework, but often we cannot know what is behind. So every service typically relies on other services to be implemented of different kinds, different infrastructures, different data sets, and things like that. And it is very difficult to know this information because it is only known to the specific providers that implement the different solutions. So for instance, in this picture, you see a lot of services highlighted and interconnected between them. But each of these services could have implemented on top of additional services. And and it is difficult to discover in a systematic way all these relationships for a lot of privacy and confidentiality concerning issues. Also, these kind of services have already in place their cybersecurity measures to protect them against attackers, but this is usually done in a fragmented way. Each provider independently managed its own security services without collaboration with the other. And the problem, and despite the fact that we have today a lot of interfaces for consuming, combining, and self-provisioning digital services, we don't have, or at least we have a very limited interfaces for also self-managing security. So the main purpose for Miranda is to overcome this limitation by providing the concept of cybersecurity digital twin. What is a cybersecurity digital twin? It is the extension of a well-known concept of digital twin applied mostly for physical systems to digital system. So here, since a digital system is already a kind of, it's not typically a physical system, it includes a lot of assets which are virtual or software-based, so it's not a physical system. The idea for a cyber security digital twin is something that is able to understand, follow and anticipate cyber threats on underlying digital systems. So basically, there are already applications of cybersecurity digital twins in the literature, but in many cases they are plain digital twins of a physical system, also including digital assets that are used to exercise specific cyber threats or cyber attacks. In our case, we want something different. So the main purpose here is to build a sort of models of the attacks strictly connected to the underlying digital systems. So the idea is a digital twin. So we want to have bidirectional flows of information, both for collecting and monitoring data and also to apply security controls on the system. And the real challenge here is the scope, because we are targeting digital service chains. So we are targeting to collect data and to apply controls in a multi-ownership environment, which is very challenging because of the different trust relationships between providers. On top of the cybersecurity digital twins, based on the advanced features it tells us, we want to improve also collaborative cybersecurity operations. So we want to revise typical detection, monitoring, response processes in order to build on the knowledge, on the specific capabilities of this digital twin. So what is the basic approach for building this concept? The idea is that each provider builds its own twins of its infrastructure, its digital assets, in terms of resources, relationships, dependencies, vulnerabilities, and so on. And then these different models are combined together to create a large digital twin over the whole computing continuum. We think that each provider has different trust requirements with the other and trust relationships with the other providers. So the idea is that this digital twin is not something that could be shared entirely. There will be some kind of opacity on the information exchanged between the providers. So providers that I trust, I can give him full visibility over my infrastructure. Provider that I don't trust, I will not give them any visibility over the underlying services and things like that. So the basic idea is depicted in the top part of this slide, where you see that the overall chain has different level of visibility. The value proposition for Miranda is that the digital twin should be proactive, pervasive, and adaptive. Proactive because we want not only to detect threats, but we want to anticipate threats. So we want to have models for predicting threat propagation. We want to have a mechanism for threat hunting, so to understand what kind of threats the system is vulnerable to in its current configuration, but also in alternative configurations. So the idea of a digital twin, as any other digital twin, is the capacity of trying and investigating alternative configurations, both in terms of service configurations and service composition, to see how the system attack surface changes. And this can be done, running these twins under different conditions can be done by using the prediction tools to emulate, to predict possible data and how they could evolve in a different manner in the future. So not only considering historical data, but also taking into account different evolutions of this data, things that we typically do with AI-based algorithms. And the other tool for investigating is the sandbox environment, which is used to replicate part or the entire services in a safe environment when we can change its compositions, we can change its configuration, and see how it behaves under the current real or alternative inputs from the real system. The second property is pervasiveness, which means that we want a system that goes into the detail of the current service composition. So, for instance, what we want to know is to build very deep graph of all assets and their relationships. For instance, we are able to discover the current compositions of Kubernetes services, to link them with virtual machines or servers that host them, to link virtual machines with the servers that host them, and also to correlate virtual machines and containers to the internal software artifacts that are using to build them. So, for instance, we map service Kubernetes containers to Linux namespaces. We map virtual machines to the hypervisors that create them and things like that. Everything is described. We try to describe them with common emerging standards like CycloneDX for the XBOM. Okay, we are working on that because we found that the current definition is mostly software oriented and does not cover well the whole range of services that are indeed deployed in a typical environment. Okay, but this is things that we are still working on. Finally, the adaptive property. We know that with service chains, because they typically use self-provisioning interfaces, they use APIs, they use service-oriented architectures, are typically change over time. So maybe I'm deploying today my service in a cloud provider infrastructure, then I have some problems there. I needed to move this to another service provider without almost, let me say, any effort, because by using the same service templates, deployment is a matter of minutes, not of hours, like in the case of configuration of a physical service. So when the configuration changes, where the infrastructure changes, probably I have different kinds of logs, different kind of services, different kind of traffic, and so we implement things like the dynamic parser generation, so the ability to automatically understand the structure of log files, so to not rely on any specific structure for parsing specific logs from a specific application. We also implement adaptivity by context-aware response, which is by mapping the current logs and the security-related events to the system topology we derive with XBOM. And we also build threat intelligence and map threat intelligence to the current system to build new stories, to understand new threats from open source intelligence and things like that. Basically, the part behind the general value proposition, we are also implementing a set of capabilities in our system related to monitoring, detection, hunting, and response. So, okay, I think I already introduced most of these. We started with a very general, not so general, but quite precise framework in mind, which reflects the general concept I described. I just described them. So we have in our idea there should be this kind of cybersecurity digital twin, which is the intermediate layer in this architecture, which is responsible for discovering the composition of the systems, its dependencies, to emulate, to predict the evolution of the system, to allow to understand how the output of this system change with different inputs or with different configurations. And this is done by directly interacting with security agents deployed in each domain. On top of a twinning layer, there is the cybersecurity processes. They are exactly the same kind of processes already found today in many applications, in many environments, but the difference is that they are enhanced to leverage these capabilities of a digital twin. Another thing is the possibility to federate these twins to build the overall large vision over the whole computing continuum. So the idea is that each domain exchanges information about the assets and dependencies in its domain with different level of visibilities based on trust concerns. And then each provider has the visibility of the whole system and can apply its own security processes. This scheme is thought both for being applied by each provider independently or also by sharing the whole model to an upper layer organization, for instance, a managed service security service provider or a national authority, a national XIRS, for investigating threats at the national or European layer. What we are now at the end of the second year of the project. So we are delivering, we are now integrating our platform. And the platform is in part already integrated, but we have still to release it. We hope that we will able to release the first version of our free platform, which will be open source and free of charge by 1 or 2 months at latest. Basically, we included support for a number of agents at the low level. Typical agents that are used today, like the bits, network monitor tools like fprobe and probe, and also the capability. This is something new that we built in our system, the capability to create XBOM of entire services, not only the software. Okay, we can integrate software BOM in our system, but we can. The main important thing is that we can discover the service composition. We use OpenC2 as the only interface to interact with different agents, and we implemented a lot of profiles, not a lot, 4 or 5 profiles, which are currently missing for controlling file log agents and the network sniffers. And we also are able to create automatically the data landing pipeline, so to automatically configure the whole pipeline that collects data and deliver it internally. Internally, we have a set of models and simulation tools for understanding which threats affects which components, to compute potential attack paths, and we have a lot of tools for investigating, like the IOC extractor, the detect mate tool to detect and automatically parsing logs, Deep Guardian with advanced AI detection algorithms, Taranis AI for building stories and exchanging threat intelligence, the threat sharing API to exchange threat sharing with other platforms like MISP, and the SID tool to detect attacks in the log of a system without AI. More tools will come in the next year. It will be integrated in the next months, so to create the full range of services and application for Miranda. As Miranda, we also integrated most of the available tools in a commercial platform, Logstail. We will release, in any case, a free dashboard, which will be available for evaluating the system and for the community to develop further systems. And we now have to integrate additional tools and systems in another commercial platform, which is Sphinx. Okay, and all these tools make use of REST-based APIs and can be easily chained to create different combinations, different services according to the needs of a specific use case owners. Finally, very quickly, in the next year, we are going to validate our solutions in 3 use cases. They are free smart city services deployed in Wolfsburg, Germany, Genoa, Italy, and Athens, Greece. Smart cities are an interesting testbed for this project because they are increasingly built with by combining services and tools from different providers, including IoT devices, LoRaWAN networks, 5G networks, Wi-Fi networks, local networks, and data sets, data sources, and things like that. A lot of things combined together, usually from different providers. The use cases owners have already replicated part of their infrastructure just to not create problems with the production environment. The production environment will only be used to collect datasets for training our ML and AI algorithms. And then in the next months, we'll deploy the Miranda agents and we'll connect the use cases with the Miranda platform to perform validation and demonstration activities. We also plan to have a demo to the upcoming CloudCom conference in Paris in October, where we are going to organize a workshop with the other projects funded under the same call. So it's an interesting venue for everyone. I invite you to participate, to submit some paper, and to come and to see our demos live. If you need to know more information about Miranda, we have a lot of socials, including a website, Twitter, LinkedIn, and the email address, and also the YouTube video. So maybe I was a bit longer than expected, but I finished, and I'm here for questions, if any.
Thank you very much, Matteo. Very interesting presentation, and maybe see you in Paris in the CloudCon. But I was wondering, are there any questions? We have still a lot of people online. Haptamiu, Manos, you have any questions for Matteo? Basically, Matteo, my question is, how do you keep the synchronization in the digital twin? So what if there is some configuration change in the cloud, maybe some Docker container and so on? What are your latency boundaries? Things like that, right? A little bit on the practical side.
Okay, for that, the answer is quite simple. For now, we use a polling mechanism to retrieve the configuration every time the central platform wants to detect any change. And so the latency is based set by the time you need to query all the components. It's a recursive process where you start from the root service, the service you know. For instance, you know that you are operating a smart city service giving citizens access to a specific web portal, and then you start from that service. You need to understand from that service which other services it builds on, so you discover recursively other services, you query them, and things like that. So for now, the basic understanding is that Kubernetes is quite fast to answer and to perform the discovery process. OpenStack is much slower. For now, we are in the range, we are just trying to estimate more precisely this in these days, but we think the order of minutes is feasible in this case. And of course, it could be improved with a push mechanism, but this is a bit more complex to implement, so we haven't implemented this yet.
If my use case needs, lower latency, I need to poll more frequently, right? To put this way, I can configure that.
Yes, but the performance constraint here is given by the time each context agent needs to answer you. If you try to query, for instance, OpenStack to know the list of virtual machines, or try to query Kubernetes to list the current containers deployed in the environment, it takes time. It's not a matter of milliseconds. It's a matter of seconds. So this is what limits the polling. And of course, there is an overhead, because every time you query the system, you waste resources there. So, okay, for the moment, we are pretty satisfied with the polling mechanism, because if you look at CycloneDex and all the other XBOM mechanisms, there is no way to automatically discover the XBOM. Usually they are published on websites and you have to download them. So the possibility to query in real time and to build the XBOM in real time, because what we do is to build the XBOM in real time. So we don't rely on static and stored information. We query the different systems and we get this information. In the next step, of course, we can integrate this. One reason why we didn't integrate the notification mechanism is that it is not yet defined in OpenC2. So we basically use the plain OpenC2 definition from the standard.
Okay, thank you. Very informative. Haptamiu, what is the question?
Yeah, Sorry, I have muted myself because there is a noise in the background, so bear with me. Thank you so much for the very interesting presentation. And what two things which captured my attention. The one is your proactive module as well as your adaptive module. And there, when you discuss, you mentioned that you anticipate events, and that is very interesting to me. That my question is how do you what you call capture the events, and how do you predict such unforeseen events based on unknown data, and how do you evaluate the impact of that prediction you made on this event?
Okay, there are two ways for supporting the prediction in our cybersecurity digital twin. One way is quite simple, it's the sandbox environment where we run the system or part of the system with different inputs. So in this case, we can have these unexpected events as a result of different input conditions, like it was a fuzzing analysis based made on the system. The second way to for the prediction is to work directly on input data, because one of the problems today is that we have only historical data that might not include everything possible event. So what we are doing is to use generative AI to be trained with a past history and to see if we can generate different and unexpected events. Honestly, I cannot give you the full scientific understanding of this because it's not my field of research. But this is something that, if you want, I can send you by putting in contact with a partner that is dealing with this issue.
I would be very interested to get more know about this, since I am doing a basic research around anticipatory AI.
Yes, there are two kinds of anticipatory events that we are trying to do in our use cases. The first one is about the traffic in a TCP/IP network, so network connections, network size, everything that could be not precisely measured in the past, and the other activity is on LoRaWAN traffic. So it's a bit different from the plain TCP/IP network. LoRaWAN has its own protocol and quite precise timing, and there is an activity in based on one use case where we are trying to predict possible evolutions of the system in the future, so that we don't need to know a priori, we don't need a lot of historical data available covering all possible situations to train the other algorithms.
May I comment, John, something? One more comment? Yeah. The present modules, they don't generalize to unknown data. That is a problem we are dealing with. Have you managed to optimize models to to generalize to unknown data not by training or by input?
No, I don't think so. But for a more precise question, we should talk with a partner that works on this item.
Okay, okay.
Thank you. Really very interesting. All the presentations were very interesting. And with that, unless we have any other questions, I would like to...
Question.
Brian? Yeah,
John, I have a question. I'd like to just, if I may, my question was really about spatio-temporal scalability, but I think we covered the temporal in the first part. But how scalable do you see this asset management system to be? Because it sounds like you're dealing with a lot of different systems.
Sorry, can you repeat the question,
How
please?
scalable? I mean, there are two aspects to it. The spatial scalability. How many systems can you deal with? It sounds like you're trying to deal with a lot of very fine granularity, a lot in your XBOMs, very, very detailed. Have you experienced any problems around that, or do you foresee any problems, or how are you managing to handle possibly millions and millions of different objects?
Okay, this is something that we need to clarify in the last year of the project with the validation phase. There are, you are right, because there are especially two big scalability problems. One is the discovery of the resources and the assets, which, as I was discussing with John, takes time to be reported by the different interfaces. I said that querying OpenStack takes around 3 seconds for a small OpenStack installation. Probably this is not linear with the size of OpenStack. And Kubernetes is a bit faster, and also in this case, probably it is only partially linear dependent. The real scalability challenge, anyway, is on attack prediction, because I didn't have time to go into the detail, but one of the things that we do is to assign to link each asset to vulnerabilities that are retrieved from the common sources like CVE and the others. But exploring all possible paths is very, very time consuming, especially with formal logic algorithm we are implementing. So with tenths of resources, it is still quite tractable. With hundreds or thousands of resources, or even millions of resources, we have probably to split the problem into multiple sub-problems, into multiple subdomains to keep it computationally feasible. But okay, this is, I don't have specific numbers for now. We have to evaluate this in the next year.
Did I understand you to say you're constructing attack graphs on top of the asset database?
Yes.
Well,
We are constructing attack graphs with a formal logic model.
Yeah. Then you have state space explosion, and that's a different kind of scalability.
We expect we expect this explosion, and this is something that we still yes.
Do you have a deliverable or something that describes system, or have you published anything?
Yes, there is a deliverable 3.1, which is about this part on the discovery and the attack graph generation, which is publicly available on our website. You can download it. The website is the one I show at the end of the project, but if you want, you can drop me an email or ask. If you don't have my mail, you can ask to John, and then I'll give you the link to download the deliverable.
Thank you, Matteo. A lot of questions in the end. That was good. Good that people stayed. So